Hello friends, welcome to my channel Learn Computer Science and Application. Today in this lecture we will study shortage of first CPU scheduling algorithm. In shortage of first scheduling algorithm हम हर एक प्रोसेस का estimated CPU time find करते हैं which is also called bus time और हम इस bus time को use करते हैं to schedule process in the priority queue जिसमें प्रोसेस जो होते हैं रेडी क्यू सीपीयू जो होता है एलोकेटेड टू द प्रोसेस किया जाता है विद मिनिमम सीपीयू बस टाइम एंड सो ऑन. अगर दो प्रोसेस अराइव करते हैं इन द क्यू विद द सेम सीपीयू बस टाइम, द प्रोसेस विच अराइव फर्स्ट विल बी एलोकेटेड द सीपीयू ऑन फर्स्ट कम फर्स्ट सर्व बेसिस, दैट इज फीफो. Two schemes for shortage of first scheduling algorithms are: first is non-preemptive scheduling and second one is preemptive scheduling. In non-preemptive scheduling, once the CPU is allocated to the process, जो process होता है is kept with the CPU until it is terminated or its transition has changed to block state. This means जब CPU को हम allocate करते हैं process को, the process is kept by the CPU until it completes its work or it is willingly surrenders or leave the CPU. In preemptive scheduling, जब एक process with higher priority comes for execution, then the process currently using the execution will be forcibly removed by the CPU so that the high priority process can come and execute first. In other words, you can say that if a new process arrives with CPU burst time less than the burst time of current executing process, तो जो current process जो होता है will be preempted or forcibly removed by the CPU so that it can be executed by the new process. इस स्कीम को हम शॉर्टेस्ट रिमेनिंग टाइम फर्स्ट शेड्यूलिंग भी कहते हैं. एडवांटेजेस ऑफ शॉर्टेज ऑफ फर्स्ट शेड्यूलिंग एल्गोरिदम्स. शॉर्टेज ऑफ फर्स्ट शेड्यूलिंग एल्गोरिदम्स जो होते हैं वो ऑप्टिमल होते हैं बिकॉज दे प्रोवाइड और दे गिव द मिनिमम एवरेज वेटिंग टाइम फॉर द गिवन सेट ऑफ प्रोसेसेस रन बाय द सीपीयू. डिसएडवांटेजेस of shortage of first scheduling algorithm. Generally, in shortage of first scheduling algorithm, it is not practical to find the CPU burst time for every process. Thus, we can only predict the amount of CPU burst time of the process run by the CPU. Arrival time. Arrival time जो होता है is the point of time in milliseconds at which a process arrives in the ready queue to get executed by the CPU. Burst time. Burst time जो होता है is defined as the time required in milliseconds by the CPU to execute the process. Burst time को हम execution time और run time of the process भी कहते हैं. Completion time. Completion time जो होता है is the amount of time जब process finishes its execution. Completion time includes arrival time plus the time when CPU executes its execution. That is, completion time is also called arrival time plus turnaround time. Turnaround time. Turnaround time जो होता है is the time interval when the process is submitted to the time of completion of the process. That is, turnaround time is equal to completion time minus arrival time. Waiting time. Waiting time is the time spent by a process waiting in ready queue for getting the CPU for execution. That is, waiting time is equal to turnaround time minus burst time. Here in this example, I have discussed an example for shortage of first scheduling algorithm. In this example, let us have three processes P1, P2 and P3. P1 have CPU burst time of 13 milliseconds, P2 have CPU burst time of 5 milliseconds and P3 have burst time for 2 milliseconds. Now scheduler schedule these processes according to their burst time as shown in Gantt chart below. In this Gantt chart below, P3 has a minimum burst time of 2 milliseconds, so it starts executing at 0 milliseconds and execute for 2 milliseconds. Now process P2 have a burst time of 5 milliseconds, which is less than burst time of process P1, that is 13 milliseconds. So P2 starts executing at 2 milliseconds and get execute for 5 milliseconds. At last, P1 starts executing at 7 milliseconds and execute for 13 milliseconds. As you can see in this above Gantt chart, waiting time processes for P1 is 7 milliseconds, P2 is 2 milliseconds and P3 is 0 milliseconds. So average waiting time is equal to 7 plus 2 plus 0 divided by 3, which is equal to 3 milliseconds. Now in this example below, I have discussed an example for preemptive shortage job first scheduling algorithm. In this example, there are three processes P1, P2, P3. P1 have CPU burst time of 13 milliseconds and it arrives at 0 milliseconds. Process P2 have CPU burst time of 5 milliseconds and it arrives at 1 millisecond. And last, process P3 have CPU burst time of 2 milliseconds and it arrives at 2 milliseconds. Now below I have designed a Gantt chart for this preemptive shortage job first scheduling algorithm. As you can see in the above Gantt chart, the scheduler takes process P1 for execution for 1 milliseconds. At time 1, process P2 also arrives and it finds that process P1 needs 12 milliseconds for execution, whereas process P2 needs 5 units of time for execution. Therefore, it preempts P1 and put it into the ready queue and takes process P2 for execution. At time 2, it finds another process P3 with 2 units of time for execution. At this moment, P2 needs 4 milliseconds of time for execution and process P1 needs 12 units of time for execution. So the scheduler puts P2 into the ready queue and takes up process P3 for execution. In this way, the processing proceeds in the order as designed in the Gantt chart above. Now here I am discussing again that turnaround time is equal to completion time minus arrival time and waiting time is equal to turnaround time minus the burst time. As you can see in this above Gantt chart, for process P1, completion time is equal to 20 milliseconds and it arrives at 0 milliseconds, and burst time of process P1 is 13 milliseconds. So turnaround time is equal to completion time minus arrival time, which is equal to 20 minus 0, which is equal to 20 milliseconds. And waiting time is equal to turnaround time minus burst time, which is equal to 20 minus 13, which is equal to 7 milliseconds. For process P2, completion time is equal to 8 milliseconds and it arrives at 1 millisecond and its burst time is 5 milliseconds. So turnaround time is equal to completion time minus arrival time, which is equal to 8 minus 1, which is equal to 7 milliseconds, and waiting time is equal to turnaround time minus burst time, which is equal to 7 minus 5, which is equal to 2 milliseconds. For process P3, completion time is equal to 4 milliseconds and it arrives at 2 milliseconds, and its burst time is 2 milliseconds. So turnaround time is equal to completion time minus arrival time, which is equal to 4 minus 2, which is equal to 2 milliseconds, and waiting time is equal to turnaround time minus burst time, which is equal to 2 minus 2, which is equal to 0 milliseconds. Now average waiting time is equal to waiting time of process P1, process P2 and process P3 divided by 3, which is equal to 7 plus 2 plus 0 divided by 3, which is equal to 3 milliseconds. Now I have described another example of non-preemptive shortage job first scheduling algorithm. In this example, there are 4 processes P1, P2, P3, P4. P1 arrives at 0 milliseconds and have burst time of 7 milliseconds. P2 arrives at 2 milliseconds and have burst time of 4 milliseconds. Then P3 arrives at 4 milliseconds and have a burst time of 1 millisecond. And at last, P4 arrives at 5 milliseconds and have a burst time of 4 milliseconds. Now this is non-preemptive FGF scheduling algorithm, which means in this algorithm, Once a process has been allocated to CPU for execution, it cannot be preempted or removed forcibly from CPU execution till the process is terminated or is converted to block state. Here I have designed a Gantt chart for non-preemptive shortage of first scheduling algorithm. In this Gantt chart for process P1, completion time of P1 is 7 milliseconds. It arrives at 0 millisecond and have a burst time of 7 milliseconds. So completion time, turnaround time is equal to completion time minus arrival time, which is equal to 7 minus 0, which is equal to 7 milliseconds. Waiting time is equal to turnaround time minus burst time, which is equal to 7 minus 7, which is equal to 0 milliseconds. For process P2, completion time is equal to 12 milliseconds and it arrives at 2 milliseconds, and burst time is equal to 4 milliseconds. So turnaround time is equal to completion time minus arrival time, which is equal to 12 minus 2, which is equal to 10 milliseconds. Now waiting time is equal to turnaround time minus burst time, which is equal to 10 minus 4, which is equal to 6 milliseconds. For process P3, completion time is equal to 8 milliseconds and arrival time is 4 milliseconds and burst time is 1 millisecond. So turnaround time is equal to completion time minus arrival time, which is equal to 8 minus 4, which is equal to 4 milliseconds. And waiting time is equal to turnaround time minus burst time, which is equal to 4 minus 1, which is equal to 3 milliseconds. Now for process P4, completion time is equal to 16 milliseconds, arrival time is 5 milliseconds and burst time is equal to 4 milliseconds. Therefore turnaround time is equal to completion time minus arrival time, which is equal to 16 minus 5, which is equal to 11 milliseconds, and waiting time is equal to turnaround time minus burst time, which is equal to 11 minus 4, which is equal to 7 milliseconds. Therefore average waiting time is equal to waiting time of process P1 plus P2 plus P3 plus P4 divided by 4, which is equal to 0 plus 6 plus 3 plus 7 divided by 4, which is equal to 4 milliseconds. In this example, I have discussed a preemptive shortage of first scheduling algorithm. Preemptive shortage of first scheduling algorithms are the algorithms in which process can be forcibly removed for execution by the CPU by a process with higher priorities. Here in this example, there are 4 processes: P1, P2, P3, P4. Process P1 arrives at 0 milliseconds and have a burst time of 7 milliseconds. Process P2 arrives at 2 milliseconds and have a burst time of 4 milliseconds. Similarly, P3 arrives at 4 milliseconds and have a burst time of 1 millisecond. And lastly, process P4 arrives at 5 milliseconds and have a burst time of 4 milliseconds. As you can see in the above Gantt chart, scheduler takes up process P1 for execution by the CPU for 2 milliseconds first. For 2 milliseconds. At time 2, P2 also arrives in the ready queue for execution by the CPU. It finds that process P1 requires 5 milliseconds more to execute by the CPU and process P2 requires 4 milliseconds to execute by the CPU. So scheduler preempts process P1 and put it in the ready queue and takes P2 for execution by the CPU for 2 milliseconds. As you can see, at time 4, P3 also arrives in the ready queue for execution. It finds that P1 requires 5 milliseconds more to execute, P2 requires 2 milliseconds more to execute, and P3 requires 1 millisecond to get executed by the CPU. So scheduler preempts P2 and put it in the ready queue and take P3 for execution for 1 milliseconds more. At last, at 5 millisecond, P4 also arrives in the ready queue for execution. It finds that P1 requires 5 milliseconds to execute and P2 requires 2 milliseconds to execute. So scheduler takes P2 for execution for 2 milliseconds by the CPU. In this way, the processing proceeds the order as designed in the Gantt chart above. As you can see in this above Gantt chart, for process P1, completion time is equal to 16 milliseconds, its arrival time is 0 milliseconds, and burst time is 7 milliseconds. So turnaround time is equal to completion time minus arrival time, which is equal to 16 minus 0, which is equal to 16 milliseconds. And waiting time is equal to turnaround time minus burst time, which is equal to 16 minus 7, which is equal to 9 milliseconds. Now for process P2. For process P2, the completion time is 7 milliseconds, its arrival time is 2 milliseconds, and burst time is 4 milliseconds. Therefore, turnaround time is equal to completion time minus arrival time, which is equal to 7 minus 2, which is equal to 5 milliseconds. And waiting time is equal to turnaround time minus burst time, which is equal to 5 minus 4, which is equal to 1 milliseconds. Similarly, we can calculate for process P3, completion time is equal to 5 milliseconds, and its arrival time is 4 milliseconds, and burst time is 1 millisecond. So turnaround time is equal to completion time minus arrival time, which is equal to 5 minus 4, which is equal to 1 millisecond. And waiting time is equal to turnaround time minus burst time, which is equal to 1 minus 1, which is equal to 0 milliseconds. And lastly, for process P4, completion time is 11 milliseconds, and it arrives in the ready queue at 5 milliseconds, and burst time is 4 milliseconds. So turnaround time is equal to completion time minus arrival time, which is equal to 11 minus 5, which is equal to 6 milliseconds. And waiting time is equal to turnaround time minus burst time, which is equal to 6 minus 4, which is equal to 2 milliseconds. Now, average waiting time can be calculated as waiting time for process P1 plus P2 plus P3 plus P4 divided by 4, which is equal to 9 plus 1 plus 0 plus 2 divided by 4, which is equal to 3 milliseconds. Thus here we can see that there is a reduction in average waiting time of this preemptive shortage of first scheduling algorithm as compared to non-preemptive shortage of first scheduling algorithm discussed in previous example above. स्टूडेंट्स, उम्मीद है आपको मेरा लेक्चर पसंद आया होगा. अगर पसंद आया है तो लाइक करें, शेयर करें, बेल आइकन को क्लिक करें और चैनल को सब्सक्राइब करना ना भूलें. थैंक्स फॉर वॉचिंग गाइस. थैंक यू.